Okay, so here is a you try. Hopefully you did give this one a try on your own just to see how far you could go. I know it wasn't in the lesson booklet. I added it in just to give you one more example in case you needed it to see the process. Okay, so we're finding the area under y equals x squared plus x from x equals 1 to x equals 3. So a is equal to 1 and b is equal to 3. So the first thing I'm going to do is find my width. So the change in x is b minus a on n. So that's going to be 2 on n. And then I'm going to figure out my height piece, okay, which is your f of a plus I change in x, just change in x, sorry. No division. I don't know what I was thinking. All right, so a is 1. So I have f of 1 plus the I width is 2I on n. So that's representing my height, and that's going to go into my function. F of x is equal to x squared plus x. So each of my x's is going to get replaced with 1 plus 2I on n. So this is equal to 1 plus 2I on n squared plus 1 plus 2I on n. So x squared plus x. Okay, so this is where you have to FOIL. Okay, so you'd get 1 plus 4I on n plus 4I on n squared plus 1 plus 2I on n, which is equal to 4I, oops, that should be squared, sorry, 4I squared on n squared plus 4I on n plus 2I on n is 6I on n plus 2. So now I have an expression for my height and my width, and I can go ahead and make my limit formula. So the third thing I'm going to do is that the area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of my width times height of each rectangle. So my width is 2 on n multiplied by my height, 4I squared on n squared plus 6I on n plus 2. And then I'm going to do some algebra. Okay, so this is equal to the limit as n goes to infinity of the sum from I equals 1 to n. I'm going to distribute that through, so I get 8I squared on n cubed plus 12I on, that's an I, n squared plus 4 on n. Okay, now what I'm going to do is separate each of those into their own sigma notation. And I'm going to just do 2 steps in one here. I'm going to take out my constants, so the 8 on n cubed. I'm going to put it in front of my sigma right away, just to reduce the number of lines of work. Okay, so I'm going to scroll. It's equal to the limit as n goes to infinity of the first one. I'm going to take out the 8 on n cubed, and it'll leave me with the sigma of I equals 1 to n of I squared, plus I'm going to do the next one in its individuality. I can take out a 12 on n squared, leaves me with the sum I equals 1 to n of just I, plus in the next one I can take out the 4 on n and leaves me with just summing up a whole bunch of 1s till n. And then I put a close bracket on all of that because I want to evaluate the limit on all of this. And what I have done is created each individual sigmas that I have formulas for on that front page. Okay, those are the 3 that I now can go to that front page, find those formulas. So the first one is your I squared. So what does that look like? That's the same as saying 1 squared plus 2 squared plus 3 squared all the way to n squared. Okay, so we're going to replace those. So this is equal to the limit as n goes to infinity of we have, it's hard for me to read on an angle here, 8 on n cubed times, the first formula is n times n plus 1 times 2n plus 1 on 6. That's your I squared. Okay, I'm still evaluating the limit on all of these. Plus 12 on n squared. The I sigma notation is n times n plus 1 on 2. Plus 4 on n multiplied by n, because the constant is 1. So c times n is, where c is 1, is just n. Okay, so now I've dropped all my sigmas, and I can start to tidy this up so that I can evaluate each of my limits. Okay, so let's see. In the first one, I can see that the n on the top can cancel and make an n squared on the bottom. Similarly, in the next one of those n's cancels, makes me an n1. And then in the end one, the n's will cancel. So as I start to write this out, the first one, 8 on 6, is 4/3. The limit as n goes to infinity of, I'm going to FOIL the top, n plus 1 times 2n plus 1 is 2n squared plus 3n plus 1, all on n squared. That's this guy. Okay, and then I'm going to do that for the next one. 12 divided by 2 is 6. I'm going to put that constant in front of this limit. And on the top, I have n plus 1 on n plus 4. And now I'm ready to evaluate my limits. So it equals to 4/3, the limit as n goes to infinity of 2n squared on n squared plus 3n on n squared plus 1 on n squared, all divided by n squared on n squared, plus 6 multiplied by the limit as n goes to infinity of n on n plus 1 on n divided by n on n plus 4. And you may want to put brackets around this. It's a lot of writing. You need a lot of paper. Okay, so what happens here? Now I can actually reduce some stuff. So in the first limit, these two pieces go to 0, and it leaves me with 2 on 1. So I get that the area is equal to 4/3 times 2 on 1 plus, in the second one, this piece goes to 0 and leaves me with 1 on 1. So 6 times 1 on 1 plus 4 on the tail. And what does this all simplify to be? So I have, let's see, 8/3 plus 10, which is equal to 38 on 3. Oops, 38 on 3 units squared. Woohoo! Give yourself a pat on the back if you managed to get that all on your own. Again, we can check our answer using our knowledge of antiderivatives. So the area to the right for this boundary 3 would be the integral from 1 to 3 of my function, which was x squared plus x, in terms of x. So take the antiderivative of this, and we would get 1/3 x cubed plus 1/2 x squared, evaluated from 1 to 3. And so what do we get here? So we get 1/3 times 3 cubed plus 1/2 times 3 squared, all of that. Subtract 1/3 times 1 cubed plus 1/2 times 1 squared. And we get that first one is 27 on 2 minus the second one, which is 5 on 6. And it turns out that that is actually equal to 38 on 3 units squared. Yay! We got a match. So we're super happy. Woo! So good luck to you guys while you do this lesson. And we have one lesson left, which is looking at a trapezoidal method. So good luck to you guys, and we I'll see you in the last lesson of chapter 10. In your show, you know, when it asks you to do a question with sigma notation, they want you to do this. You can check your answer certainly with this definite integral method, but you do need to show us understanding of this sigma notation method where you take the limit and work through all the crazy expansion.